Welcome to the course on advanced power electronics. We will have a lecture 5 on choppers, DC choppers. And well, it comes in the category like a DC-DC converters, these choppers. A typical block diagram of the DC-DC converter. So normally they are used also sometime with along with the single phase or three phase supply, which use uncontrolled rectifier. After that we have a filter, and then we use the DC converter to feed the load, to feed the regulated DC power to the load. Well, the DC-DC converter we normally classified into three categories. First is the chopper, which normally used for deriving the current source, and non-isolated DC-DC converters, which is used to derive a voltage source, and again isolated DC-DC converters, which also derive for deriving a constant voltage source feeding different kind of load. Like, so this is a broad classification. So we call it DC-DC converters. So first category current source converter like a chopper. It's classified into six category: class step up, step down, step up, and then two quadrant chopper of class C and class D, then four quadrant chopper and multi-phase chopper. So we classified the chopper into six categories. Then we have a voltage source converters, which classified into two categories: now isolated DC-DC converter, starting from buck converter, boost converter, buck boost converter, buck half bridge converter, then buck full bridge converter, then boost full bridge converter, then cup converter, epic converter, and zeta converter. Similarly, we have isolated DC-DC converter, voltage source converters, which again divide into many categories like buck forward converter, boost forward converter, then flyback buck boost converter, then buck half bridge converter, buck full bridge converter, boost full bridge converter, and buck push pull converter, and boost push pull converter, then cup converter and epic converter, and followed zeta converter. So of course today we like to cover the first category, which is called choppers. So these choppers, DC choppers, are normally used to convert constant DC voltage to variable DC voltage for realizing a DC current source, and it is considered a DC converter equivalent to similar to a transformer with a variable turns ratio. The output DC voltage is varied through a solid state switch in pulse width modulation, pendulum control at constant or variable frequency switching. The applications of these DC-DC choppers are like DC motor control in locomotive, then subway cars, battery-operated pallet trucks, forklift lift trucks, electronic boards, submarine, battery-operated fans and small fans in cooling, computers, and toys. Then typical examples you can say the DC motors control in locomotive, then subway cars, where this DC, then forklift trucks where we use the choppers, then electric boards, then submarines, then battery operated fans, of course the computers, then battery operated toys. So well, coming to now solid state switch used in choppers. So earlier we were using the thyristor with force commutation, which is now obsolete because the force commutation were having the additional cost as well as the reliability issues. Sometimes commutation failure is there. Apart from that, it limits the switching frequency. So now people are not using this. So we use for very high power rating GTO, great turn of thyristor, and of course the frequency limitation is below 1 kHz. Then for medium frequency we use the IGBT insulated gate bipolar transistor and up to frequency of 20 kHz. And for high small power rating and up to 100 kHz we use the MOSFET to realize this choppers. Like, so now coming to types of choppers. Typically step down class A, we call it class A chopper, then step up class B chopper, two quadrant class C chopper, and two quadrant class D chopper, then four quadrant class E chopper, and multi-phase chopper. Now coming to circuit topologies of choppers. So this is your step down or class A choppers, where you can call it if the, of course with the assumptions, if output load current is typically continuous, then the relation for output voltage is the D duty cycle of the typically of the pendulum switching of the switch, D into V in. So it means you can by varying the duty cycle from D0 to 1, you can control the output voltage from 0 to V in. Then the another is the typically the step up chopper, where again if current inductor current is continuous, then this relation is valid, V equal to V in upon 1 minus D, with the assumption of course you neglect the, you consider the device ideal and other component also, inductor also ideal. So here also you varying the D, you can boost the voltage. I mean, of course there is a limit that you cannot boost a very high also, but of course we use this chopper also for typically like regenerative braking of DC motors. Like, then the step pump chopper typical example, you can see how it is really regenerative take place. In this DC motor have a large inductance, so because of this, when we switch on the switch, you have a increased di by dt. You are sorting the back EMF in this DC motor, and which energy is stored in the inductor. So when you switch off, the inductor stored energy along with the back EMF. This becomes more than the DC source voltage, so it boosts the voltage, and you have a regenerative braking for using this boost converter or boost chopper. Then we have a 2-quadrant chopper. This 2-quadrant chopper, of course, you can step down as well as step up. Both the functions are in this chopper. Then you have a typically circuit topology of this 2-quadrant chopper, where you can have typically the step down operation, and you can of course feed back the energy back when you switch off the devices, throw out the energy, go back to the source like on. Then the 4-quadrant chopper, this is looks to like an edge bridge, and it can be operated with all 4-quadrant, all the 4 choppers which we discussed earlier. So you can have a bidirectional power flow in the load. You can have regeneration also, forward regeneration, backward regeneration, as well as forward motoring and when reverse motoring as far as DC motor is concerned. And if you have a typically a kind of DC source, you can even like a battery, you can charge or you can discharge, of course, with the bidirectional current. So you can have a power flow in this manner for this. So this 4-quadrant chopper is very versatile chopper. You can call it called class A chopper. Then we have a multi-phase choppers. So you are for this multi-phase chopper is applicable again for many. So like we have a step down chopper. The advantage of typically putting multi-phase, you can have a phase shift here. So output voltage will be D1 plus D2 into V in. So the advantage here that you can have a phase shift also in that, and the ripple in the output load current can be reduced in this case. And similarly, you can reduce the ripple from the input source. So because if one chopper is drawing the current, if other not drawing, for other sometimes the second can certainly take the current. So you can increase the current in the load typically by applying the voltage typically from here. So this really makes the ripple current in the load substantially low. And so you can share virtually you are sharing the current among the different multi-phase choppers. Like these are another typically 3-phase choppers. So you can reduce again here. You can increase the current in the load by feeding by all the 3 choppers or multiple choppers. Like here you can call it a P chopper. So it give a large current in the load. Sometimes you have DC voltage source, but motor voltage, you want to use very large current for the starting of DC motor, so that can be done by this multi-phase choppers. Like so now coming to a quadrant operation, as we call it, like in class A you have only the positive voltage, positive current, and class B you have a positive voltage and negative current, and class C you can have a positive voltage and current can be positive or negative. So you can have a 2 quadrant first and second, similarly as what was discussed. And class D have a positive and negative voltage, but current will be positive, and you can have first and 4th quadrant. And class C chopper can operate in different way, like positive voltage, negative voltage, and positive negative current. So you can have all 4 quadrant, 1, 2, 3, 4 quadrant operation with the class C chopper. So coming to mathematical analysis of the chopper circuits. So first taking example of step down chopper. So for continuous conduction, the chopper output voltage is independent of the output current, and it has 2 operating modes. In the first mode, the solid state switch is and diode switch is on and diode is off, and the current flows from source to load, as you can see during the on period, and during off period the diode conduct like on also. So this mode 1, when the switch is on and power flows from typically from through the switch to the load. And second mode, the switch is off, so source is cut, and the stored energy in the inductor circulate the current in the load. So you get a continuous load current like in that case. So during second mode, the solid state switch is off and load current flows the freewheeling diode, and in majority of the load or circuit time constant TL by R is quite high compared to the chopping period, resulting in linear rise of the load current with time and linear fall in the second mode of operation. Now typically if you looking in different modes, the equation, so chopper output voltage equation can be written here, V equal to V in into T on divided by T on plus T off, or Vn equal to D, where the T on is the on period and T off is the off time, and you can call it T on plus T off equal to T, that is equal to 1 by F, where the F is the switching frequency of the switch. Like So T is the total chopping period, F is the switching frequency, and D is the duty ratio, that's T on upon T. Now you can see how the waveform look. I mean, in case of this, in continuous conduction mode of this step down chopper, so you have input voltage, then you have input current. That's also become discontinuous because when switch is off, you are not drawing any current from the source, but the output voltage, you can call it have a small ripple across the load, and then you have output current which is almost continuous with a small ripple because of the inductive filter may be a part of the load. Then the inductor voltage which flick certainly positive to negative, and the inductor current it's also remain always, that's typically the load current, so it remains almost continuous with very less ripple. And then you have a switch voltage which comes across when switch is off, and then you have a switch current, it's also when switch is on, and then the diode voltage, it comes typically, you can call it's a zero during conduction, when otherwise it's a negative voltage comes across the diode, and you have a current only when it conducts through it, otherwise it has a zero current. So now typically in step down chopper in mode 1, so you can have a load current for the first mode may be achieved like Vn equal to R I on plus LD I on upon dt plus E. I mean, the majority of cases we have a load which have a back EMF like or it may have a battery charging. So both the cases the equation are valid. The initial condition of this I t equal to 0 is I minimum, that is a minimum current. I mean, because of the field wing action at the end of field wing action. So the solution of this goes I on equal to I minimum e to power minus T into R upon L and plus V in minus E upon R 1 minus T to power T R upon L. So first mode is for that is you can say solution of the fourth equation which is in the fifth, and for the finding out the minimum value we can have a conditions typically the boundary condition in that. So we can say if for 0 to T on period, that is dt, at the end of this mode the load current is I on T equal to V on equal to dt, that is the I max, because the energy is fed from during this period from the source to the load. So now the load current in second mode may be achieved from the volt current ampere, because where the field diode conducts, so you have applied voltage 0. If you neglect the drop of the diode, so it becomes R I off plus L d I off upon dt plus E equal to 0. So when initial current equal to I max and resetting the time original, that's T equal to 0. Current I off in the second mode can be expressed I off as a function of T, that is I max e to power minus T into R upon L and minus E upon R in bracket I minus E to power minus T upon R upon L. So this second mode is only for 0 to T off, that is equal to 1 minus D into T, and at the second mode the load current is I of T equal to T off equal to I minimum, and the relations between minimum and maximum current form can be written I max equal to I minimum e to power dt upon TA plus V in minus E divided by R into 1 minus E to power d T upon TA, and I minimum equal to I max E to power 1 minus D into T upon TA minus E upon R 1 minus E to power minus 1 minus D T upon TA, where TA is the time constant L upon R, and solving these equation we can get I max and I minimum. So I minimum is V in upon R into in bracket divided by E to minus D minus X minus 1 divided by E to power X minus 1 minus E upon R. So where X is T upon TA or T RL upon R upon L, ratio of chopping period to the circuit time constant. So I max equal to V in upon R E to power minus dx minus 1 divided by E to power minus X into minus 1 divided by minus E upon R. So now you can call it delta max. Delta I will be I max minus I1. So that becomes VIN. We have IN upon R in bracket 1 minus E to power minus kx plus EX E to power minus X minus E minus 1 minus dx divided by 1 minus E to power minus X. And you can say how typically with the duty cycle your normalized ripple current, that's a delta I upon V in upon R, it varies for the different duty cycle and with the different T upon TA. So you can say if we have a typically varying the duty cycle, is how it is the variation is there for this ripple current like. So conclusion from this figure is the ripple current reduces to 0 as D goes to 0 and D goes to 1, and differentiation of equation of delta I reveals that the maximum ripple current occurs at D by 2, and the longer the load L upon time LR constant TA, the lower will the output ripple current, because the stored energy in the inductor will be high, and the higher the switching frequency 1 upon T, the lower will be the output, your output ripple current. So now coming for maximum ripple current relation, so we can take a derivative of this ripple current with respect to time. So it results e to power minus dx minus e to power 1 minus dx into x or equal to 0, but called minus d equal to minus 1 minus d or d equal to 0.5. So thus the maximum current ripple will be at d equal to 0.5, and it is delta I max equal to V upon R into 10 hyperbolic in bracket R upon 4 FHL, or that becomes V in upon R in bracket 1 minus e to power minus 0.5 T upon TA, or divided by 1 plus e to power minus 0.5 T upon TA. So for the assumption 4FL, if we consider the 4FL is much higher than R, and then 10 hyperbolic will be 5 will be equal to 5, so maximum ripple current may be approximated delta I max equal to V in upon 4FL. So for the continuous conduction, the various relation can be derived. In equal to dIO, and from the power equality we can call P in equal to V in into In equal to PO equal to VO In. So input effective resistance can be made equivalent to I in equal to V upon IO or equal to R upon D, and inductor average current will be I average equal to IO average, and inductor minimum current will I minimum or inductor maximum current will be equal to I maximum. So inductor RMS current, that I RMS will be equal to I minimum square plus in bracket I max minus I minimum square by 3 plus I minimum in bracket I maximum minus I minimum 3. So input RMS source current will be I in average D I0, and input source minimum current will be I in minimum, that is 0 because it starts from 0, and input source maximum current will be I max equal to I max, and solid state switch average current will be again same I average D I0, and solid state switch maximum current will be IS max equal to I max, and solid state RMS current will be I S RMS D to power 0.5 bracket I minimum square plus I max minus minimum to power square by 3 plus I minimum I max x minus I minimum by 2 power 0.5. So switch average voltage will be P 1 minus D into V in, and switch minimum maximum voltage V S max will to V in, and you can call it switch RMS voltage V in under root 1 minus D. So diode average current will be ID average equal to 1 minus D I0, and diode maximum current will be ID max equal to I max. So diode RMS current will be IS RMS under root 1 minus D I max square plus I maximum I minimum square by 3 plus I max minus I minimum. So diode average voltage will be VD average equal to minus dV in, and diode maximum voltage will be VD max minus V in, and diode RMS voltage will be VD RMS equal to V in under root D. And typically for discontinuous current mode of this step function, which happens either your duty cycle is low, or typically your inductance is quite low, or the back EMF is high. So these are the conditions where you have a chances of going to discontinuous mode. So for low value of duty ratio at low output voltage and high value of battery voltage or back EMF E, the load current may become discontinuous, as you see the boundary here. I mean as a function of V upon V as a ratio, and into the typically the your I upon LB max. I mean for the input constant voltage. So there is a boundary how it really goes for discontinuous condition. For other region it remains continuous. And this again the typically if output voltage is constant, how it is with the ratio of input to output voltage, this chances of discontinuous goes again in the as a function of this your inductor maximum current. Now coming to step down chopper for discontinuous current, as you can see in the waveform. I mean when you typically your duty cycle is low, so and inductance is also low, then chances of and back EMF is high, then you have a discontinuous current. Clearly you can see typically in the load also it touches the 0 because the back EMF it counters the voltage like So now coming to a analysis in DCM mode. For the case of discontinuous current, I minimum is 0. So IO on T equal to in bracket V in minus E upon R to power 1 minus E to power T upon TA. So moreover for 0 to T from 0 to TC, that I of at t is equal to 0, which results in t is equal to L upon R logarithmic in bracket 1 plus R I max upon E, and at t equal to dt, the current I on is at I on t equal to I max in bracket N minus E divided by R 2 into 1 minus e to power minus tx, and after substituting for I max, the critical time constant Tc is Tc equal to L upon R logarithmic in bracket 1 plus V in minus E divided by E into 1 minus e to power minus x. So however, for boundary condition of continuous conduction for I minimum greater than 0 or equal to 0, that is e to power minus dx minus 1 divided by e to power x minus 1 minus e upon v in, that should be positive greater than 0 or equal to 0. So this provides the value of ratio e upon v in equal to z, where z is equal to e upon v in and must be lesser than e to power minus dx minus 1 divided by e to power x minus 1. So now coming to the filters, design of filters for step-down chopper. To improve the performance of the chopper at the input source and output load, a set of filters is used. The input filter is normally LC filter, and output filter is generally an inductor, which may be a separate inductor or part of the load, or combination of external inductor and inductance of the load. And the objective of output filter is to make an ideal ripple-free DC current in the load, or at least continuous current. So a typical example, you can say how the input filter, after the source we have a L and C. Why C is there? Because switch is off, then still LC circuit will remain, make the continuous current in the source. And then output, the inductor, because of filling action, when switch is off, filling action make the output current continuous. So this work as a, this output inductor work as a filter, like for step-down chopper. Now with the output filter, normally the design of this output filter inductor is made for the specified current level in the load current, which is also dependent on the chopper frequency F, and the maximum current ripple occurs at d equal to 0.5. So e to power minus 0.5 x equal to 1 minus y upon 1 plus pi, where x equal to t upon tau and tr upon L, or equal to r upon Lf, and y equal to delta I max r upon V. So from this equation, we may be modified t upon ta to ln in bracket 1 plus pi divided by 1 minus y, and equal to r upon f in bracket 2 logarithmic 1 plus y divided by 1 minus y. So now coming to the design of input filter. So it is observed, as you can see in the diagram, second diagram on the right side, it is observed that without input filter, supply current is same as chopper switch current, which varies from 0 during turn off to the maximum load current during on period of chopper. And this type of fluctuating current from the DC supply, which may cause undesirable effect on voltage fluctuations, electromagnetic interference, radio frequency influence, and supply voltage distortion and additional heating. So the nth harmonics in the DC supply is at INS equal to in bracket XC upon N divided by NXL minus XC upon N into ICHN, and where XL equal to 2 pi FL, X equal to 1 upon 2 pi FC, N is the order of harmony. So INS equal to ICHN divided by 2 pi NF square LC minus 1, or ICHN equal to 1 upon in NF upon FR square minus 1. So where FR is the regional frequency of the chopper, that's 1 upon under root 2 pi under root LC. So the two frequency F and FR must be different to avoid the resonance, which results in large oscillation of the supply voltage. So normally F is selected more than the twice of FR, and in such cases the supply harmonics may be approximated INS equal to FR divided by NF square into ICHN. So for an ideal chopper with perfect input and input source and the output load, shown in the figure, the following relation is V voltage ratio is V upon V in equal to D, and current IO upon I in equal to 1 upon D, and average switch current I average D into I0, and RMS switch current IS I0 under root D, and average diode current is I0 1 minus D, and RMS diode current is equal to I0 under root D. So now coming to step up chopper. So class B chopper is used to step up the variable voltage, as you can see in the diagram. When we close the switch, the current flows through the, load is short circuited through across the inductor, and it increases the current. And when you switch off it, the drop of the inductor reverses and it adds to the voltage and becomes more than the source voltage and power flows. So we have a two mode: when switch is on, when switch is off. So when switch is off, then only energy flows from load to the source. Like so, now the waveform for step-up chopper, you can clearly see how it is your input current is continuous with a small ripple. Then output voltage also has some ripple. Then output current is also same as the typically have a ripple. Then inductor current, inductor voltage, inductor current, and switch voltage, switch current, and diode voltage, diode current all are shown here. So coming to this analysis of step-up chopper in continuous conduction mode, so average input voltage can be expressed in terms of output. So Vin equal to VO T off divided by T on plus T off. So that becomes VO into 1 minus T. So alternately, a boost inductor is huge in step-up chopper, does not store any energy under the steady state condition in P11 period. It means the energy which is stored in on period same is relates it releases during off period. So therefore the energy stored in the input inductor during the on period must be equal to off period, considering the current in the inductor remains constant. So V in IOT on equal to VO minus V in into IT off. And the solving it, the relation between input output voltage is V equal to V in bracket T on plus T off divided by T off, or equal to V in T upon T minus T on, or equal to V in divided by 1 minus T. So for deriving current relationship, it is considered that an input practical inductor has a small definite resistance. So assuming an ideal filter at the output voltage at output high voltage, a volt current relation during turn on period is L di on plus upon dt plus I on equal to V in, and with the initial condition I on equal to I minimum at t equal to 0. So with the initial condition I on equal to I minimum at t equal to 0, the volt current relation during turn on period is as VO minus Vn equal to R I of plus L di of upon dt. So with the initial condition I of equal to I max at t equal to 0, so I max and minimum are the minimum maximum current, and these maximum minimum current values are to be same under the steady state condition in different chopping cycle. So thus the solution for equation with the power initial condition is I max equal to V in upon R into e to power minus T on upon Ta plus I minimum e to power minus T on upon Ta. So where T equal to L upon R, and I minimum is in bracket V in minus VO divided by R, and in bracket 1 minus e to power minus T of upon Ta plus I max e to power minus T of upon Ta. For further solving the equation, I max and minimum can be calculated as I max equal to V in upon R minus VO upon R in bracket e to power minus T on upon Ta minus e to power T upon Ta divided by e to power minus 1 upon e to power minus T upon T. So I minimum is V in upon R minus VO upon R, and that is in bracket 1 minus T of upon Ta divided by 1 minus T e to power T divided by Ta. So the peak to peak current is delta I equal to I max minus minimum, that is V upon R in bracket 1 plus e to power minus T upon Ta minus in bracket e to power minus dt upon Ta plus e to power minus 1 minus dt upon Ta divided by 1 minus e to power minus Ta upon T minus divided by Ta. So condition for maximum current ripple can be derived in the similar manner, and it appears at d equal to 0. So the average input current can be derived I in average equal to V in minus V S average divided by R, and in bracket V in minus 1 minus T VO upon R. So coming to step up chopper in discontinuous current mode, the input current drawn from the DC source of the low voltage may become 0 before the end of off period of the chopper. So the boundary condition between continuous and discontinuous current may be achieved I minimum equal to 0, which results in V in upon VO equal to in bracket 1 minus e to power T of upon Ta divided by 1 minus e to power minus T upon Ta. So however, DCM may be avoided either by increasing the value of inductance or frequency of the chopping or both. And these are typically the reason here for step chopper for discontinuous current. So here also when you have a typically the duty cycle you can call it, and with the inductance low value, then chances of discontinuous is more. Now coming to filters of step up choppers, so normally a high value of inductor is used in the input, which is the low voltage side, to reduce the current ripple into a specified value, and a CL filter is used on the output side of the to have a ripple free current and ripple free voltage. So the following relation can be derived as In upon I equal to 1 upon 1 minus D, and average input current is I in average equal to I upon 1 upon D, and switch average current is S average equal to IO D upon 1 minus D, and switch average voltage is your Vs average V in equal to VO upon 1 minus into 1 minus D, and switch peak voltage is Vs equal to VO. Diode average current is ID equal to ID average equal to IO, and diode maximum current is ID max equal to I max, and diode average voltage VD average equal to dV0, and diode peak voltage or VD max equal to V0. So now typically this is typically how your waveform looks like, typically in continuous, and this continuous mode for this typically for this step of chopper for class B choppers. So clearly how your current as well as voltage are there, as well as along in relation to the typically background. So coming to the typically the analysis during the switch on period when V equal to 0, IO plus LD IO upon TT equal to E, which leads IOT equal to I minimum E to power minus T upon T max plus E upon R to into 1 minus E to power T upon TA, where your T varies 0 to T on, and during the switch off period when V equal to Vs equal to Ri 0 plus LDI 0 upon dt equal to plus Vs, which leads IOT equal to I max E to power minus T upon TA minus in bracket E minus Vs divided by R into 1 I minus E to power minus T upon TA, where your T varies from 0 to Tc, and I max equal E upon R, Vs upon R, E to power T into capital T upon TA minus E to power minus T upon TA divided by 1 minus E to power T upon TA, and I minimum E upon R minus Vs upon R into 1 minus E to power T plus T on upon TA divided by 1 minus E to power T upon TA. And this is typically the two quadrant chopper. I mean like Q1, Q2 as shown in the quadrant operation. So you can just see how the typically positive current or typically positive or really the negative current goes with always the positive voltage. So two modes are shown here. The first mode when switch is on, you have a similar to like a step down chopper, and the mode 2 when the lower switch is on, the current goes back to the source as it is shown here. That goes to second quadrant operation, and you can see the waveform how for quadrant 1 and quadrant 2 are there for voltage and current and source current typically in both the cases. So for possible output modes can occur depending on the relative polarity of the maximum and minimum currents shown in figure as shown. So I minimum is greater than 0, I max greater than 0, and I0 is also more than 0. So when the minimum current as the average output current is greater than 0, the chopper is active in the first quadrant, and the switch T2 and out D2 do not conduct during the any period of the operating period, and I minimum is less than 0 and I max is greater than 0 or I0 is greater than 0. So when the minimum current is negative but the maximum positive current is larger in absolute magnitude than the highly inductive load, the average output current is greater than 0 and the chopper operates in first quadrant. If the load is not highly inductive, the boundary is determined by the average output current I equal to greater than 0. So various circuit waveform are shown in the typically figure. So the third condition is I minimum less than 0, I max is greater than 0, and I0 is less. So highly inductive, it is magnitude of the negative peak is greater than the positive maximum. The average is less than the 0 and the chopper is operating in the regenerative mode. And in quadrant 2, if the load is not highly inductive, the boundary is determined by the average output current less than 0. So for the fourth condition, I minimum less than 0, I max also less than 0, and I0 also less than 0. So all are negative. When the maximum current and the average current are both are negative, the chopper is operational in the second quadrant. Since the load current never goes positive, switch T1 and diode D1 never conduct as shown in figure. And typically, now coming to typically two quadrant, this typically a two quadrant operation of this is four quadrant chopper, how really operate for second and fourth quadrant like T on and DT on this different operations, and these are the typical waveform for quadrant 1, quadrant 4, and you have a operation when what devices are conducting when T1 and T4 are 0, T1, D4 0. I mean this explain the different operating condition for regeneration also. There are two types of switching. Multi-level switching is when both switches are controlled independently to give the all three output voltage, three levels, that plus minus V0, plus minus Vs and 0, and bipolar switching, two level switching, then both the switches operate in unison and they turn on and to turn off to the only 2 voltage output state, and the it will call bipolar, that is plus Vs and minus Vs. So it's called unipolar switching and bipolar switching. And this is typically your 4 quadrant operation, the mode, and typical multi-level, 3 level, as you can see in the left side waveform, and how 3 level waveforms really are there for with the PWM, and the multi-level with the case of again of 3 level for different quadrant. So when first quadrant and then typically second quadrant also. So the output voltage switches plus minus Vs, and the relative duration for each state depends on the magnitude of modulation index, and if D equal to 0, then T1 and T4 never turn on, since T2, T3 conduct continuously, which implies minus Vs across the load. At the other extreme condition, if D1 equal to 1, then T1 and T4 are continuously conducting and the Vs is impressed across the load. If D equal to half, then T1 and T4 are turned on for half the period T, and while T2 are for remaining half the period, the output voltage is minus for half and plus half for, and the average output voltage therefore 0, but the disadvantageously the output current needless ripple about the 0 with the average value. So the chopper output voltage is defined in terms of triangular reference wave delta V delta greater than 0, so V equal to minus Vs, and delta V delta is less than delta, and V equal to minus plus Vs. And this is the typically in the operation for bipolar in 2 level, when it operates only the pure unipolar mode. So you will have a positive negative voltage applied across the load, and you have a large ripple current and switching, and the output ripple is also equal to switching frequency. In previous case, it was the double thought. So this is in the case of 2 level output voltage and is lower than 0. So now coming to the multi-phase chopper, as you can see, 2-phase chopper and N-phase chopper. So multi-phase chopper is a chopper which has several identical choppers operated in parallel and phase shifted from each other, and these may also be configured in different quadrant operation. They offer the advantage of reduced ripple current and increase in ripple frequency, resulting in reduction in supply harmonic current. They are preferred in large power rating when either use several solid-state devices in parallel or use multi-phase chopper, which avoids the problems of matching of dynamics and static characteristics of several devices in single chopper. So each chopper in P-phase chopper is operated at same frequency and duty cycle. So you start off switching in phase shifted by T upon P second and 360 by P in terms of angle. The effect of phase shift on current waveform can be observed as an increase in the ripple frequency. So you can just see how it's typically phase shifted for all 3 phase choppers. Phase shifting causes the, you can call it the load current, the ripple as well as the conduction of the diodes of different phases, so in different operating modes. So the number of choppers are to be simultaneously on simultaneously at any instant of time. So it dependent on the value of duty cycle. So for duty cycle 0 to 1 upon P, there is an interval when only one chopper switch is on and all other choppers are off, are filling mode, and during this period the net load current rising to maximum value Imax. Followed by this, there is an interval when all chopper switches are off and all phase diodes are filling. So during this period, net load current is decaying towards minimum value of I minimum. So in this fashion, it can be generalized that for any value of D, varying between Q minus 1 by P to Q by P, where Q is the positive integer less than or equal to P, there is 2 modes of conduction as Q choppers are on and load current is increasing towards I max, and only Q minus 1 chopper on and load current decreasing to I minimum. So where P is the number of phases while Q is the number of the phase conducting. For writing the basic relations, it is considered that Q phases are conducting and Q minus Q phases prevailing, diodes are conducting. So for such conditions, these equations are valid. Ri1 plus LDI by dt plus RL, IO plus LTIO upon dt equal to Vin. And similarly, it goes to typically for your all the choppers, the equation valid for up to P choppers. For the case where your typically P choppers are on, and then equivalent comes R1 IO equal to L1 TIO upon dt equal to V1, and where R1 is equal to R plus PRL, where L1 is L plus PLL, and V1 equal to P Vin. So this equation the volt ampere equation is applicable to the condition of increasing IO when Q chopper switches are on. Considering this period Ti of increasing current, so Ti equal to dt minus in bracket Q minus 1 P into T, or equal to T equal to D minus Q minus 1 upon P. And considering the reference time t equal to 0 at the instant of rising with initial condition as I equal to I max and at t equal to 0. And based on this, the solution of the volt ampere equation is I equal to I minimum e to power minus t upon ta plus e upon r1 in bracket 1 minus e to power tau minus t minus ta, where equivalent time constant is t a equal to L1 upon r1, and the maximum current occurs at t equal to IA, therefore I max equal to V upon R1 in bracket 1 minus e to power Ti upon Ta plus I minimum e to power minus Ti upon Ta. So during the period of decay of load current IO, Q minus 1 switches are on and other phase choppers are failing. So duration of this period is from turn off switch to turn on Q plus 1 switch, which is at Td equal to Q upon P into T minus dt and T in bracket Q upon P minus D. So during the decay of current, only Q minus P equations will have V in on R on right hand side and remaining are having 0. So by adding all the equations, resulting equation comes R1 I equal plus L1 di upon dt equal to V2, and where V2 equal to Q minus 1 into V in. So considering a new reference for the period of decay of current, the initial conditions of this equation above volt ampere equation, let's say I equal to I max at t equal to 0, solving the equation again the same voltage decaying for decaying period current I equal to I max e to power minus t upon tau plus V2 upon R1 in bracket 1 minus e to power t upon Ta. So this current decaying to minimum current I minimum at t equal to dd and I minimum equal to I max e to power t td upon Ta minus V2 upon R1 in bracket 1 minus e to power minus td upon Ta. So solving these equation for minimum maximum current I max upon V in upon R1 in bracket Q minus e to power minus T upon Ti upon Ta minus e to power T upon Pta divided by 1 minus e to power T upon Pta. So I minimum is P in upon R1 in bracket Q minus 1 minus e to power Td minus Ta divided by 1 minus e to power T upon Pta. So relation between P and Q can be written as Q minus 1 divided by P, the duty cycle varies minus Q minus 1 divided by P to Q by P. So T by P is the duration of the output current ripple, which is as T upon P equal to Ti upon Pd. So average value of the output voltage and currents are V equal to D Vin minus R I upon P, that is IORL, and IO equal to D Vin divided by RL plus R divided by P, and V equal to D Vin RL upon divided by RL plus R divided by P. So for the load having battery or backup, the equation volt ampere equation may be further modified to single equivalent chopper. So I max equal to minus P upon R1 plus V in upon R in bracket Q minus e to power Ti upon Ta minus e to power minus T upon Pta divided by e to power 1 minus e to power T upon Pta, and I minimum equal to P upon R1 plus V in upon R1 in bracket Q minus 1 to 1 minus e to power Td upon Ta divided by 1 minus e to power T upon Pta. So for boundary condition between CCM and DCM having I minimum equal to 0, it results E upon P equal to in bracket Q minus in bracket 1 minus e to power Ti upon Ta divided by 1 minus e to power T upon Pta divided by P. So coming to now numerical examples. So numerical example 1, in the battery operated car, battery voltage 144 volt and it employs a DC chopper with the armature resistance of 0.52 ohms through the step up DC chopper, and during regenerative braking when car is moving downhill at some speed, its back EMF is 120 volt and the braking motor current is 15 ampere. Calculate the duty ratio, the value of peak RMS and average current in the battery, and the value of peak RMS and average average voltage and current of the solid state switch and diode in this typically on a step up chart. V equal to E minus IRA, so that V comes putting a value 116.25 volt and V battery is V upon 1 minus D, so it comes typically with the putting value D comes 0.19, and battery parameters I in equal to IP equal to 15 ampere, I in average 1 minus D into IA, that's 12.15, I in RMS under root 1 minus D into IA 13.5 ampere. So the switch current and switch voltage, so switch current here peak is I equal to 15 ampere, IS average D into IA 2.85, RMS is under root DIA, that is 6.54, and the voltage is Vs equal to Vin equal to 144, Vs average equal to 1 minus T into Vin, 116.64, and Vs under Vs RMS equal to under root 1 minus T Vin, 129.6. So similarly for diode and voltage and current, ID peak is IA 15 ampere, ID average 1 minus DIA 12.15, and then ID is under root 1 minus DIA, that is 13.5, and VD peak is minus VD 144, and VD average D minus 125, and VD. So now coming to the second example, a first quadrant DC chopper fitting a DC motor at the output current is constant due to large inductance of motor, so that maximum input current ripple takes place at D equal to 0.5, and design at the input filter with switching frequency of 400, armature current is 100 ampere, and if I1 RMS is 10 of the average current, let the available capacitor R of 1 microfarad and can take 5 ampere. You can see the circuit with the input filter for the chopper, step down chopper for DC motor current. So I in average is D average, and I in RMS under root DIA. So I input ripple is under root in bracket under root DIA square minus DIA square. So that becomes IA under root D minus D square. So taking a typically the derivative of this I ripple square, so it becomes I into 2 minus D. So and then taking this, so it becomes D equal to 0.5, and I equal to I in 4 upon pi IA 2 pi n sin omega t plus sin 3 omega t, and I in average ID 100 into 0.5, that is 50 ampere, and I in RMS is you are putting a value come 40.1733 ampere. So now but input AC current not to suppress 10% of DC current. So in RMS is I average 10 upon 100, that's 5 ampere. I XC upon XL minus the IRMS, so that 5 you putting value, so it comes X equal to 10C, and IC equal to XL upon XL minus XC into IN. So IC1 becomes 50 ampere, but maximum ripple current is 5 ampere, therefore 10 capacitors can be connected in parallel. So it's equivalent to 10 microfarad, so XL equal to 10 XC, so L comes 0.1582 1 millihenry. Coming to numerical example third, a DC step down chopper control electric train is fed from a 175 volt DC source. The minimum effective on period is steady by 30 microsecond. If the chopper frequency 1 kilo, what is the minimum possible output voltage? So V in was 1750, T on is TDT 30 microsecond, F is 1.5 kilowatt, T equal to 1 upon F 0.0667 millisecond, D equal to T on upon T, so that is 0.045. So V output is DV in, so that is your 78.73 volt. So coming to number example 4, a battery powered chopper fed DC motor driven pallet truck is running at a constant speed. The battery voltage is 112 volt and motor vacuum is 60 volt. The chopper frequency is 2 kilowatts and the duty ratio is 80%. The motor resistance 0.8 ohms and inductance 0.25 millihenry. Calculate the peak RMS, average RMS motor current and the peak RMS value of current ripple of the motor. So getting this relation I max equal to V upon R into 1 minus e to power t 1 upon t divided by 1 e to power t upon t minus e upon r. Putting a value, it comes like your 51.3 ampere, 2 ampere. And similarly, putting a value in the relation of minimum current, it comes 16.96. And I average from the relation of VO minus ER upon R, it comes to 37 ampere. And IORMS, putting the value for this triangular wave, it comes 35.5 ampere. And ripple current, I max minus I minimum, it becomes 34.36 ampere. Coming to numerical example 5, the 4-phase chopper is operating 125 Hz at a duty cycle of 0.55. These choppers are having an inductor of 5 millihenry and their resistance of 0.5 ohm. So this chopper is feeding RLE load having a R 5 ohm, L 5 millihenry and equal to 120 volt. The DC supply 240 volt. Calculate the ripple current in load. Frequency of output ripple current, average voltage across the load resistance, average load current, values of peak RMS and average voltage and current of solitary switch and diode, and value of E at which the load current will become just discontinuous, and the value of duty cycle at which the load will become just discontinuous with equal to 120. So calculating the tau, equivalent tau, it comes to putting a value Ls plus Ls upon N divided by R plus Rs upon N, it's 1.22 millisecond, and D1 typically comes here 0.895. So hence the actual duty ratio becoming less than D1. So therefore it becomes I max, putting for it becomes DCM. So I max calculated from the relation, it comes 22.78, and delta I equal to I max, that is in discontinuous mode, it comes 22.78, and frequency of output ripple is 125 Hz. So I equal to V minus upon R, and V equal to dV in 1 minus Tx upon E. So calculating from this relation, Tx comes like 7.78 millihenry, and the output voltage comes 135.45. IU becomes, putting a value 3.015 ampere, and voltage across the load resistance IOR, that comes 15, typically 15.075 volt. Now I equal to 3.015, so we can calculate the Vs peak, V equal to V in, that is 240 volt, Vs average equal to 1 upon T, and putting value 104.55, and Vrms, putting the value, it comes 157.09, and Vd peak comes 240 volt, Vd average comes putting a value 137.55, and Vd RMS comes putting value 179.15, and Is peak is I max by 4, so it's 5.695. Is average comes putting a value 1.58, and Is RMS comes 2.45, and I diode peak divided by 4, that 5.695 ampere. ID average bring a relation value 1.2 ampere, and the ID RMS comes 2.1. If D equal to 0.55, putting the value of this, E comes 12.22, and D1 comes typically 0.895. So coming to numerical example 6, the step down chopper has a V in equal to 220 volt, F is equal to 1 kilohertz, RL load R10 and L10. Calculate the duty for the average load current to be 11 ampere, the output average voltage. So V in equal to 20, all data are given. So for I equal to 11, V equal to IOR, so it's 110, and D comes here 0.5, and output average voltage will be 4.5, that's 110 volt. So example 7, the DC step chopper has input DC source voltage and current of 120 and 10 ampere. The duty cycle is 50%. The input filter inductor has a very high inductance and resistance of 1.5 ohm. The output of the chopper has the ideal LC interrupt. Calculate the output voltage and the output current. So V in 120 volt, I in 10 ampere, duty cycle 0.5, R in 1.5 ohm. The output voltage will be V in minus, putting a relation, it comes 210 volt, and output current with the relation comes 5 ampere. So coming to numerical example 8, electric car employs a DC motor and it is fed from 96 volt battery through a DC step down chopper. This chopper sets a fixed duty frequency of 2 kHz. The motor circuit has a resistance of 0.08 ohm and inductance of 0.15 millihenry, and it has a vacuum of 50 volt running at some speed. So calculate the minimum duty ratio of the chopper below which it will operate in discontinuous mode, and what is the maximum possible vacuum at 50% duty ratio to operate chopper just in discontinuous. So given the data here, all data for minimum duty ratio, I minimum 0, V, so putting value, it comes D equal to 0.5531, and if D equal to 0.5, putting value, E comes like 44.74. So coming to your example 9, for the buck converter, R equal to your 1 ohm, D equal, V equal to 0, V equal to 10, F equal to 4 kilowatt by the off period. So putting the value, typically T of comes 187.5 milliseconds. And coming to number example 10, these are the references which we have used for this. Thank you very much.